So far we studied the motion of objects while trying to eliminate or minimize the effects of friction. Recall that we minimized the effects of friction by either using air, or oil lubrication, or by using frictionless wheels and frictionless pulleys. Now we are going to study how friction affects the motion of objects. We will learn how to take into account the effects of friction, while predicting the motion of objects. In order to do that, we must perform a physical experiment, and then from that experiment we can derive the mathematical theory of how to account for friction. The simplest experiment to isolate the effect of friction is studying the motion of a block moving on a frictionless surface, under the action of an external force. Let's design an experiment to study the motion of a block on a frictional surface. In order to study the effect of friction on the motion of the block, we have to apply a force on the block. Preferably this force should be constant, in order to eliminate the effect of the change of the force on the motion of the block. In order to produce a constant force, we can pull the block, using a body of a known mass, suspended vertically, so that it is under the influence of gravity. Since the value of the mass is constant, and the acceleration of gravity is constant, then, the value of the force, which is also the weight of the body, is constant. We connect that body to the block, using the rope pulley arrangement shown here, such that the force in the rope is equal to the weight of the body. In order to simplify the experiment, we use a rope and a pulley that are very light. Thus, we can neglect the masses of the rope and the pulley. Also, to simplify the experiment, we will use a flat surface and pull the block with a force that is parallel to the surface. Next, we will draw a free body diagram for this system. Let's draw a free body diagram for body A. We cut the rope just to the right of body A. Then we place on the cut surface on body a force pointing to the right, with magnitude F rope A. Using Newton's third law, we place on the other side of the cut surface an equal and opposite force. This force also has a magnitude of F rope A, but is pointing to the left. Then, we can write Newton's second law for body A as ma times the acceleration vector is equal to the sum of the forces. The forces acting in the x direction are F rope A, acting in the positive x direction, and the unknown friction force, acting in the negative x direction. And so ma times the acceleration in the x direction is equal to F rope A minus F friction. In the experiment that we will be conducting, we are going to measure acceleration versus the value of the applied force F rope A. And from that, we can get the value of the friction force. The forces acting in the y direction are the gravity force, ma times g acting down, and the normal reaction force of the track, n, acting up. Therefore, ma times the acceleration in the y direction is equal to minus ma times g, plus n. Body A cannot move in the y direction, because it is in contact with the horizontal track, therefore the acceleration of body A in the y direction is 0. Then 0 is equal to minus ma times g plus n, which means that the normal reaction force between the block and the surface, n, is equal to the weight of body A, ma times g. Now let's draw a free body diagram for body B. We cut the rope just above body B. Then we place on the cut surface on body B a force pointing up, that has a magnitude equal to F rope B. Using Newton's third law, we place on the top side of the cut surface an equal and opposite force, so that force also has a magnitude equal to F rope B, but is pointing down. Then, we can write Newton's second law for body B as mb times the acceleration vector is equal to the sum of the forces. Since there are no forces acting in the x direction, then A sub bx is 0. The forces in the y direction are the gravity force, mb times g acting down, and F rope B acting up. Therefore, mb times A sub by is equal to minus mb times g, plus F rope B. In summary, we have three equations that describe the motion of this two-body rope pulley system. Since the rope and pulley have negligible mass, then, the tension in the rope is constant along the length of the rope. Therefore, F rope A is equal to F rope B, and we can just replace them both with F rope, which is the tension force in the rope. Equation 2 is Ma times Aax is equal to F rope minus F friction. Equation 3 is mb times aby is equal to minus mb times g, plus F rope. We can then subtract equation 3 from equation 2. And we get that Ma times Aax, minus mb times aby, is equal to mb times g, minus F friction. If the rope stays in tension, i.e. F rope is bigger than 0, then Aax is equal to minus aby, which we can just write as A, where A is the acceleration of body A or body B. This implies that Ma plus mb, times A, is equal to mb times g, minus F friction. And this implies that A, is equal to mb times g, minus F friction, divided by Ma plus mb. This equation gives the value of the acceleration of body A or body B. Note that the acceleration is constant. We can also rewrite this as F friction is equal to mb times g, minus Ma plus mb, times A. The tension in the rope can be obtained from equations 2 or 3. Using equation 2, we have F rope is equal to Ma times A, plus F friction. And using equation 3, we have F rope is equal to mb, times g minus A. Note that the two equations give the same value for F rope. You can verify this by plugging the expression for A into these two equations, and seeing that they give the same expression for F rope. In the last slide, we derived an equation for the acceleration of a block of mass ma moving on a frictional surface and being pulled by a force that is parallel to the surface using a vertical weight of mass mb. The equation is A is equal to mb times g minus F friction divided by Ma plus mb. We rewrite this equation to give the value of the friction force as a function of the acceleration. The friction force is equal to mb times g minus Ma plus mb times the acceleration A. Thus, if we know Ma, mb and the acceleration, then we can use this formula to find the friction force. In this experiment, we will vary the mass of the block, Ma, and the mass of the suspended weight, mb. Then, we will experimentally measure the acceleration of the block for each combination of Ma and mb. Note that we can easily vary Ma by adding extra weights on top of the block. And similarly, we can easily vary mb by adding extra weights on top of it. Then, we will use this formula to calculate the friction force between the block and the surface for each combination of Ma and mb. From the calculated values of the friction force, we can come up with a theory of how to model the friction force for a block moving on a frictional surface. under the action of a force that is parallel to the surface. We first set ma to 0.1 kilograms and mb also to 0.1 kilograms. Then, we release the weight mb and let the force of the weight act on the block. The block and weight will move. We measure and plot the position of the block as a function of time, x of t, in the shown graph. We can then calculate the velocity of the block. Recall that velocity is the time derivative of position. If we have discrete values of the position at many points in time, separated by a time step delta t, then the velocity can be numerically calculated as v is equal to position at time t plus delta t, minus the position at time t, divided by delta t. From the plot of v versus time, we see that the velocity of the block is a straight line, with a certain slope. Recall that acceleration is the time derivative of velocity. Therefore, the acceleration can be numerically calculated as a is equal to v at time t plus delta t, minus v at time t, divided by delta t. Since the velocity curve is a straight line, then the acceleration of the block is a constant that is simply the slope of that line. We find that the constant acceleration of the block, when ma is 0.1 kilograms and mb is also 0.1 kilograms, is equal to 3.43 meters per second squared. We put this value in the table. Next, we change the value of ma to 0.2 kilograms and keep mb at 0.1 kilograms. We again release the weight mb. The block and weight will move. We measure and plot the position of the block as a function of time, x of t, in the shown graph. Then, we get the velocity and acceleration as we did before, and plug the constant value of the acceleration that we get into the table. We find that the acceleration is now 1.31 meters per second squared. Next, we repeat the experiment with the value of ma set to 0.3 kilograms and keep mb at 0.1 kilograms. We find that the acceleration is now 0.24 meters per second squared. Next, we repeat the experiment with the value of ma set to 0.4 kilograms and keep mb at 0.1 kilograms. We find that the block does not move, which means that its acceleration is now 0 meters per second squared. For any value of ma larger than 0.4 kilograms when mb is 0.1 kilograms, then the acceleration of the block is 0. Next, we repeat the experiment while setting mb to 0.2 kilograms and varying ma between 0.1 and 1.2 kilograms. We obtain the shown values of the acceleration. Next, we repeat the experiment while setting mb to 0.3, 0.4, and 0.5 kilograms, and again varying ma between 0.1 and 1.2 kilograms. We obtain the shown values of the acceleration. You can use the stepper buttons below to change ma and mb, and see how the position, velocity, and acceleration curves change. When you wish to continue with the lecture, press the play button. In the last slide we experimentally found the acceleration for different values of ma and mb, and also plotted it. Now we can use the friction force formula to calculate the friction force. So for any value of MA and MB, we will get a friction force. For example, if MA is 0.1 kilograms and MB is 0.1 kilograms, we can plug in the acceleration of 3.43 meters per second squared, and we get a friction force of 0.29 newtons. We can then plot friction force versus MA. For MB equals 0.1, 0.2, 0.3, 0.4, and 0.5. Note that if the block is not moving, in other words if the acceleration of the block is 0, then the friction force is simply mb times g. So when mb is 0.1, the friction force is 0.1 times 9.8, which is 0.98 newtons. And when mb is 0.2, the friction force is 0.2 times 9.8, which is 1.96 newtons. And when mb is 0.3, the friction force is 0.3 times 9.8, which is 2.94 newtons. If the block is moving, in other words if the acceleration of the block is not 0, then the value of the friction force is the same for any value of mb. For example, when MA is equal to 0.1, the friction force is equal to 0.29. And at MA equal to 0.2, the friction force is 0.59. And similarly, for MA equal to 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0, 1.1, and 1.2. Also, the friction force increases linearly with MA. You can use the stepper buttons to change MA and MB, and see how the friction force changes. When you wish to continue with the lecture, press the play button. From the block on a frictional surface experiment, we can draw the following two conclusions. If the block is not moving, in other words, if its acceleration is 0, then the force of the weight mb times g is not large enough to overcome the friction force. In that case, the value of the friction force must be equal to the tangential force that is pulling the block, mb times g, in order for the net force on the block to be 0. If the block is moving, then the force of the weight, mb times g, is large enough to overcome the friction force. In that case, the value of the friction force is independent of mb times g, and only depends on the value of ma. The following model satisfies the observed values of the friction force. The friction force is equal to the tangential force pulling the block, mb times g. If mb times g is less than a constant mu times the normal reaction force N between the block and the surface, in that case the block is stationary. Since the friction force is equal and opposite to the tangential force pulling the block. On the other hand, the friction force is equal to constant mu times N. If mb times g is greater than mu times N, in that case the block is moving. Since the net force on the block is equal to mb times g minus mu times N. The value of mu that satisfies the results in our experiment is 0.3. Let's now verify that our friction force model satisfies the observed value of the friction force. If ma is 0.1 and mb is also 0.1, then the normal reaction force N is simply 0.1 times g, or 0.98 newtons. Mu times N is 0.3 times 0.98, or 0.294. mb times g is 0.1 times 9.8, or 0.98 newtons, which is larger than mu times n. Therefore, the friction force is equal to mu times n, or 0.294 newtons. And this agrees with what we previously obtained using the shown formula. So now we have a way of calculating the friction force, if we know Ma and Mb. The friction force is equal to the minimum of the tangential force pulling the block Mb times g, and the constant mu times the normal reaction force between the surface and the block. The constant mu is called the coefficient of friction. It depends on the materials at the interface surfaces between the block and the surface. Mu can be experimentally calculated for pairs of various materials. Based on our friction force experiment for a block moving on a frictional surface, under the action of a force that is tangent to the surface, we can derive the following simple friction force model, for a particle moving on a frictional surface, where the particle in this case is the block. The friction force is equal to the minimum of the net force tangent to the contact surface, that we denote by T, and the product of a coefficient of friction, mu, and the net normal force between the contact surface and the particle, that we denote by N. Note that in the shown figure, N is equal to mg, because the surface is horizontal. This model assumes that there are two conditions for the friction force. First, if the tangential force pulling the particle is not large enough to overcome the friction force, then the friction force is simply equal and opposite to the tangential force, such that the particle does not move. And second, if the tangential force pulling the particle is large enough to overcome the friction force, then the friction force is equal to the product of a coefficient of friction mu, and the normal reaction force between the surface and the particle. In this case the particle moves, since the tangential force, T, pulling the particle, is larger than the friction force. In summary, if the applied force T is less than mu times n, then the particle will remain stationary. But if the applied force T is larger than mu times n, then the particle will move. In order to understand how friction works, we need to look at the interface surfaces between the two contacting objects, at a microscopic scale. On a microscopic scale, a surface that may appear smooth has hills and valleys that can range from 1 molecule high to several thousand molecules high. The hills are called asperities. When the two surfaces are in contact, the asperities interlock between the two surfaces. When we apply a tangential force to the block, the normal contact forces between the asperities on both surfaces prevent motion of the block. In that case, since the block is not moving, this means that the friction force is equal to the tangential force. However, if we increase the magnitude of the tangential force, when the tangential force is larger than the product of the friction coefficient mu, and the normal reaction force n, the asperities either break, or deform to allow motion of the block. If we increase the normal force, n, with which the block is pressing against the surface, then the surface asperities interlock more tightly. So, now we need a larger tangential force to break and slash or deform the asperities, in order to move the block. Note that this explanation for the friction force based on surface asperities is actually a little simplified. There are other interaction processes between two surfaces that may occur during frictional contact. Those include chemical bonding and electrical interactions. Suppose we use a block that has the same mass as our previous block, and that is made of the same material, but that has a smaller contact area with the surface. We can do this by making the block taller, such that the volume of the new block is the same as the volume of the old block. How does the change in contact area affect the contact force? There are two main effects that influence the friction force. First, the new block has a smaller contact area with the surface. Therefore we expect the smaller block to interact less with the surface, since there are fewer asperities in contact, and thus have a smaller friction force. Secondly, if the mass of the new block is the same as the mass of the old block, then the normal contact force, N, which is equal to the weight of the block, m times g, is the same for both blocks. The contact pressure P is defined as the normal contact force N divided by the contact area A. Therefore a smaller contact area, while keeping N constant, means a higher contact pressure between the block and the surface. So the new block has a higher contact pressure, since its surface area is smaller. Higher contact pressure implies that the asperities are packed closer together, which means a larger friction force. It turns out that these two effects approximately cancel each other out, such that the friction force is independent of the size of the contact area between the block and the surface. Since the friction force is equal to mu times N, and N doesn't depend on the contact area, then the value of mu doesn't depend on the size of the contact area either. In fact, the friction coefficient, mu, only depends on the two materials at the interface between the two objects in contact. We can experimentally verify that the friction force does not depend on the contact area by performing the friction force experiment of the block on a frictional surface. Using a taller block, that has the same mass as the original block but that has a smaller contact area with the surface. If we perform the friction force experiment for the tall block, we will find that the position versus time curve for this block is the same as the position versus time curve for the original block that has a larger contact area. This means that the acceleration of both blocks is the same, which implies that the friction force for both blocks is the same. This in turn implies that the friction coefficient is the same for the new block, that has a smaller contact area with the surface, and for the original block, that has a larger contact area. We experimentally found a simple model that gives us the value of the friction force for a particle on a frictional surface, where the particle in this case is a block. In that model, the friction force is equal to the minimum of the net tangential force on the particle, and the product of a coefficient of friction mu, and the normal reaction force between the particle and the surface. We also found that the coefficient of friction, mu, does not depend on the size of the contact surface, and only depends on the two materials of the contact surfaces. If we do the friction experiment more carefully, we will find out that the value of the coefficient of friction mu also depends on the relative speed between the particle and the surface. When the relative speed between the particle and the surface is 0, or very close to 0, mu has a certain value that is called static friction coefficient, mu sub s. If the relative speed between the particle and the surface is greater than 0, then the value of the coefficient of friction for most materials goes down slightly, which means that the friction force is reduced. The value of the coefficient of friction when the relative speed between the particle and the surface is greater than 0, is called the kinetic friction coefficient, mu sub k. Mu sub k, for most contacting material pairs, is less than mu sub s. Therefore, we can rewrite our friction force model more accurately as follows. If the relative speed between the particle and the surface is 0, then the friction force is equal to the minimum of the net tangential force on the particle, and the product of the static coefficient of friction mu sub s, and the normal reaction force between the particle and the surface. If the relative speed between the particle and the surface is greater than 0, then the friction force is equal to the product of the kinetic coefficient of friction mu sub k, and the normal reaction force between the particle and the surface. This model assumes that the kinetic coefficient of friction does not change with relative speed. This is in general approximately true for low relative speeds between the two contacting surfaces. For high relative speeds between the contacting surfaces, the kinetic coefficient of friction for some material pairs decreases as the velocity increases, and for other material pairs, increases as the velocity increases. For most problems in this course, we will assume that the static and kinetic friction coefficients are equal. This means that we will use the simpular friction model. In that case, we just refer to the coefficient of friction as mu, without a subscript s or k. This is a good approximation for a large number of common materials. In general, the kinetic friction coefficient is on the average about 80% of the value of the static friction coefficient. This is why if you are pushing a box on a horizontal surface, it is hard to get the box to start moving. But once the box starts moving, you can keep it moving using a smaller force than the force you used to get it to start to move. For most common material pairs, the static and kinetic coefficients of friction are between 0 and 1.2. Here is a list of static and kinetic friction coefficients for some common pairs of materials. Steel on steel has a static friction coefficient of 0.74, and a kinetic friction coefficient of 0.57. Steel on aluminum has a static friction coefficient of 0.61, and a kinetic friction coefficient of 0.47. Steel on copper has a static friction coefficient of 0.53, and a kinetic friction coefficient of 0.36. Steel on ice has a static friction coefficient of 0.1, and a kinetic friction coefficient of 0.05. Ice on ice has a static friction coefficient of 0.1, and a kinetic friction coefficient of 0.03. Glass on glass has a static friction coefficient of 0.9, and a kinetic friction coefficient of 0.4. Teflon on Teflon has a static friction coefficient of 0.04, and a kinetic friction coefficient also of 0.04. Teflon on steel has a static friction coefficient of 0.05, and a kinetic friction coefficient also of 0.05. Rubber on rubber has a static friction coefficient of 1.16, and a kinetic friction coefficient of 1.1. Note that for rubber on rubber, the static and kinetic coefficients of friction are both greater than 1. Rubber on concrete has a static friction coefficient of 0.9, and a kinetic friction coefficient of 0.8. Rubber on wet concrete has a static friction coefficient of 0.3, and a kinetic friction coefficient of 0.25. Rubber on snow has a static friction coefficient of 0.3, and a kinetic friction coefficient of 0.2. Note that for some pairs of contacting materials, the kinetic and static friction coefficients are the same, such as Teflon on Teflon and Teflon on steel. And for some other pairs of contacting materials, the kinetic friction coefficient can be less than 50% of the value of the static friction coefficient, such as glass on glass. In this example, we want to calculate the acceleration of a block of mass m, moving on an inclined plane. The plane has an inclination angle of theta. Then, assuming the coefficient of friction is 0.3, it is required to find the acceleration of the block, for theta is 10, 30 and 50 degrees. We start by drawing a free body diagram of the block. The forces acting on the block are the normal reaction force between the block and ground, N, normal to the plane, the gravity force mg pointing down, and the friction force, which is tangent to the surface and acting in the opposite direction to the motion of the block. We can write Newton's second law for the block in the x, y coordinate system as m times the acceleration vector is equal to the sum of the forces on the block. The forces in the x direction are the friction force times the cosine of theta minus n times the sine of theta. The forces in the y direction are the friction force times the sine of theta plus n times the cosine of theta minus mg. Alternatively, we can write the equation of motion for the block in a frame with its x-axis tangent to the plane, denoted as x prime, and its y-axis normal to the plane, denoted as y prime. In this case, the equation of motion can be written as mass times the acceleration vector is equal to the sum of the forces on the block. The forces in the x prime direction are the friction force minus m times g times sine theta. The forces in the y prime direction are n minus m times g times cosine theta. Note that the equations of motion written in the xy frame are the same as the equations of motion written in the x prime, y prime frame. But, in the case of a block moving on an inclined plane, it is more convenient to use the x prime, y prime frame because it is aligned with the plane. And so we have the shown two equations of motion for the block. The acceleration of the block normal to the plane is 0, since the plane restricts the motion of the block. Note that using the x prime, y prime frame allows us to use the fact that the acceleration of the block normal to the plane is 0, to simplify the equations of motion. So n minus mg cosine theta is 0, which means that n is equal to mg cosine theta. The tangential force to the plane pulling the block down is equal to mg sine theta. From our friction model, the friction force is the minimum of T and mu n. Substituting the expression for T and for n, we have the minimum of mg sine theta and mu mg cosine theta. Substituting the expression for the friction force into equation 1, we get mat is equal to the expression for the friction force minus mg sine theta. Then cancelling m and factoring out g, we get the shown expression for the acceleration in the tangential direction to the plane. Therefore we have the following two cases. The acceleration tangent to the plane, at, is 0. If the sine of theta is less than or equal to mu cosine theta. Or in other words, if the tangent of theta is less than or equal to mu. On the other hand, if the sine of theta is bigger than mu cosine theta. Or in other words, if the tangent of theta is bigger than mu, then at is equal to g times mu cosine theta minus sine theta. We can write the equation of motion of the block from the last slide as shown, and we assume that mu is equal to 0.3. Suppose theta is 10 degrees. The tangent of 10 degrees is 0.176. Which is less than mu of 0.3. Which means that the acceleration of the block at is 0, in other words the block is not moving. Next, suppose theta is 30 degrees. The tangent of 30 degrees is 0.577. Which is bigger than mu of 0.3. Which means that the tangential acceleration of the block, at, is equal to 9.8 times mu cosine 30 minus sine 30, which evaluates to an acceleration of minus 2.35 meters per second squared. Note that the minus sign means that the block is moving and accelerating in the negative x prime direction. Finally, suppose theta is 50 degrees. The tangent of 50 degrees is 1.19, which is bigger than mu of 0.3, which means that at is equal to 9.8 times mu cosine 50 minus sine 50. This evaluates to minus 5.62 meters per second squared. In the last example of a block on an inclined plane, we derived the equations of motion of the block as shown here. The block tangential acceleration along the plane inclination direction is equal to 0. If the tangent of theta is less than or equal to the coefficient of friction mu, where theta is the plane inclination angle with respect to the horizontal plane, and the block tangential acceleration is equal to g times mu cosine theta minus sine theta, if the tangent of theta is greater than mu. Therefore, if we start with the inclination angle of the plane at 0, so that the plane is horizontal, then slowly increase the inclination angle, the block will be on the verge of moving, when the tangent of the plane inclination angle is equal to mu. The plane inclination angle at this point is equal to the inverse tangent of mu. This angle is called the friction angle. It is formally defined as follows. The friction angle is the inclination angle of a plane with respect to the horizontal, at which a block resting on the plane will be on the verge of moving. Note that once the block actually starts to move, the value of the plane inclination angle at that point is actually slightly higher than the friction angle. The coefficient of friction between two materials can be found by doing an experiment to find the friction angle. Let's perform an experiment to measure the coefficient of friction between the block and the plane. We start from the block being horizontal. Then, we slowly increase the plane inclination angle. We can see that the angle at which the block starts to move is approximately 10 degrees. This is the friction angle. The tangent of this angle is the coefficient of friction mu between the material of the block and the material of the plane. So in this example, since the friction angle is approximately 10 degrees, then the coefficient of friction is equal to the tangent of 10 degrees, which is equal to 0.176. Now you try the experiment. Adjust the angle of the plane, so that the block is just about ready to slide down. Then calculate the value of the coefficient of friction between the block and the plane, and type it in the shown box. When you wish to continue with the lecture, press the play button. Let's look at the two-body rope pulley experiment, with one mass suspended vertically, and one mass moving with friction on an inclined horizontal track. The two masses are connected using the rope pulley arrangement shown in the figure. We assume that both the rope and pulley are massless. Body A has a mass ma, and body B has a mass mb. If the inclination angle is 15 degrees, mass ma is 1 kilogram. Mass mb is 0.5 kilograms. Then calculate the acceleration of body A, corresponding to a friction coefficient between body A and the track of 0.1, 0.2, and 0.3. Assume that positive motion is pointing upwards. In any friction problem we need to determine the direction of motion, because it is the direction of motion which determines the direction of the friction force. The direction of the friction force is always in the opposite direction to that of the direction of motion. So for mass A, if the motion is going uphill, then the friction force will point downhill. And if the motion of mass A is going downhill, then the friction force will point uphill. Recall that we determined the equations of motion of the system if the friction is zero. We found that A is equal to mb minus ma sine theta times g divided by ma plus mb. So we have two cases. Case 1. If the acceleration is positive, this means that the direction of motion is uphill, which means that the friction force must point downhill. And, case 2. If the acceleration is negative, this means that the direction of motion is downhill, which means that the friction force points uphill. Let's draw a free body diagram for body A. For the case where the acceleration without friction is positive, we cut the rope just to the right of body A. Then we place on the cut surface on body a force pointing to the right and up, with magnitude F rope A. Using Newton's third law, we place on the other side of the cut surface an equal and opposite force. This force also has a magnitude of F rope A, but is pointing to the left and down. There is a friction force, which points in the opposite direction to the motion. Then, we can write Newton's second law for body A in the x'-y' frame as ma times the acceleration vector is equal to the sum of the forces. The forces acting in the x' direction, which is the tangential direction to the track, are F rope A minus mag times the sine of theta minus F friction. As we've seen before, the friction force is mu times n. The forces acting in the y' direction, which is the normal direction to the track, are n minus mag times the cosine of theta. And so we have the shown two equations. There is no acceleration in the normal direction, and so n minus mag cosine theta is equal to 0, which means that n is equal to mag cosine theta. Substituting this expression for n into equation 1, we get the shown expression, which we can rewrite as F rope A is equal to ma times aat, which is the acceleration of body A along the track, plus g sine theta, plus mu g cosine theta. Case 2 is for the case when the acceleration without friction is negative, which means that the friction force points upwards, in the same direction as the motion. This case is exactly like case 1, except for the differences in sign, for all the terms with mu, as shown here. So we have F rope A is equal to ma times aat plus g sine theta minus mu g cosine theta. Now let's draw a free body diagram for body B. We'll go over it quickly since you've already seen this before. We cut the rope just above body B. Then we place on the cut surface on body B a force F rope B pointing up. And then using Newton's third law, we place an opposite force F rope B pointing down. Then, we can write Newton's second law for body B In the xy coordinate frame, there are no forces acting in the x direction, and so a sub bx is 0. The forces in the y direction are the gravity force, mb times g acting down, and f rho b acting up. Therefore, mb times a sub by is equal to minus mb times g, plus f rho b. Let's calculate the equations of motion for case 1 and case 2. In summary, for case 1, we have three equations that describe the motion of this two-body rope pulley system. Equation 1 is ma times aat plus g sine theta plus mu g cosine theta is equal to f rho a. Equation 2 is mb times aby is equal to minus mb times g plus f rho b. Equation 3 is f rho a is equal to f rho b, which we can just refer to as f rho. We can use equation 3 to rewrite equations 1 and 2 as shown here. We can then subtract equation 5 from equation 4. And we get that ma times aat plus g sine theta plus mu times g cosine theta minus mb times aby is equal to mb times g. If the rope stays in tension, i.e. f rope is bigger than 0, then aat is equal to minus aby, which we can just write as a, where a is the acceleration of body A or body B. This implies that ma plus mb times a is equal to mb minus ma times sine theta minus mu times ma times the cosine of theta times g. Note that the acceleration must be greater than 0. This implies that a is equal to the maximum of the shown expression, and 0. This equation gives the value of the acceleration of body A or body B. Note that the acceleration is constant. Note too that acceleration cannot be negative, otherwise the friction force would be driving the motion. But friction force cannot drive the motion, it can only oppose any existing motion. In other words, friction can only slow down the object or stop it from moving. The tension in the rope is the force F rope A, which is also equal to F rope B, and can be obtained from equations 4 or 5. Using equation 4, we have F rope is equal to ma times A plus g sine theta plus mu times g cosine theta. And using equation 5, we have F rope is equal to mb times g minus a. Note that the two equations give the same value for F rope. Case 2 is just like case 1, except for the differences in sign, for all the terms with mu, as shown here. Also the acceleration must always be negative. This implies that a is equal to the minimum of the shown expression, and 0. In order to find the acceleration with friction, the first thing we need to do is to calculate the acceleration without friction. If the sign is positive, then the acceleration with friction will also be positive, and we can use equation 1. If the sign is negative, then the acceleration with friction will also be negative, and we can use equation 2. So in this example, we are given an angle of 15 degrees, mass A of 1 kg, and mass B of 0.5 kg. Substituting these values, we find that the acceleration without friction is 1.57 meters per second squared. Since this number is greater than 0, we will use equation 1 to calculate the acceleration with friction. We were asked to find the acceleration for 3 different values of mu. For mu equals 0.1, The acceleration evaluates to 0.945 meters per second squared. For mu equals 0.2. The acceleration evaluates to 0.314 meters per second squared. And finally, for mu equals 0.3. Even though the shown expression evaluates to negative 1.7, the acceleration is 0, because it can't be negative. Note that as you increase the friction coefficient, the acceleration decreases. From an acceleration of 1.57 when mu equals 0, all the way down to an acceleration of 0, when mu equals 0.3. If we solve equation 1 for mu, when the acceleration is 0, we will get that mu equals 0.25. This means that any mu bigger than or equal to 0.25, will give an acceleration of 0. For the shown crate, resting on a flat surface, if we try to move the crate by pushing it from behind or pulling it, then we need to apply a force that is greater than the coefficient of friction between the crate and the surface, times the normal reaction force between the crate and the surface, where N is equal to the weight of the crate, mg. If we put the crate on a cart with wheels, then it will be much easier to move. Why is this so? The wheels of the cart can roll, and therefore the effective coefficient of friction between the crate and the surface is much lower. This coefficient of friction is called the coefficient of rolling friction. Typically the coefficient of rolling friction is 0.002 for metal wheels on a metal surface, 0.01 for a cart, and 0.02 for rubber tires on pavement. This is much lower than the regular coefficient of friction, which for the crate on a flat surface, is typically 0.3. For example, if the mass of the shown crate is 100 kilograms, then the weight of the crate is mass times g, which is 100 times 9.8, which is 980 newtons, or 100 kilogram force. Without a cart, we need a force of 0.3 times 980, which is 294 newtons, or 30 kilogram force to move the cart. With the crate on a cart, we need a force of 0.01 times 980, which is 9.8 newtons, or 1 kilogram force to move it. So we can see that the force required to move the crate is 30 times less, using a cart with wheels. This is why we use wheels to move heavy objects.